Hello and welcome. Luke Skywalker and Darth Vader are sitting around a Christmas tree. Vader says,
Luke, I know what you're getting for Christmas.
and Luke says, "How do you know?" Vader replies,
Because I felt your presence.
In this second of the trilogy of packets, we're going to look at the second derivative and their graphs. Let's get started. So in the last packet, we looked at how the first derivative tells us if the graph of a function is increasing or decreasing. It also helped us find the maxes and mins, the high points and the low points of a graph. Now with the second derivative tells us the rate at which the first derivative is changing, which tells us how the graph bends. So in the first picture on the left side, we have an upward facing parabola. And one thing is, if you notice, as you move from left to right across this parabola, I don't know why I have my headphones on. That was weird. As you move from left to right across this parabola, notice that the slopes of the tangent lines are always increasing. We can write even that the slopes of the tangent lines are increasing. That means that the rate at which the first derivative is changing is positive. If the first derivative values are getting bigger and bigger and bigger as you move from left to right, because the slopes of the tangent lines are getting bigger and bigger as you move from left to right, then that means that the rate at which the first derivative is changing is positive. So in those cases, you get a situation where the curve bends like this. It bends in this kind of upward manner. If you imagine riding a surfboard, if the red line, the tangent line, represents the surfboard as you're riding the graph from left to right, the graph wave, you can imagine, then as you're riding along this wave, the nose of the surfboard is going up. Right? So the nose of the surfboard at first was down, then at the bottom it's going to be a little bit higher up, and then as you keep moving to the right, the nose of the surfboard will get higher and higher. More and more up, I should say. So in those cases, we would say the graph is concave up. Now in the picture to the right, notice that the tip of the surfboard, the nose of the surfboard, starts off being really up, and then as we're moving from left to right, the nose of the surfboard is going down. So even though the graph is increasing, the nose of the surfboard is going down, which says that the first derivative is going down, or in other words, decreasing. So here, where the slopes are decreasing, the first derivative is decreasing, and you get a curve that we call concave down. So again, tying it back to the second derivative, if the second derivative is positive, that means the rate at which the first derivative is changing is positive. So that means the first derivative values are increasing, and the graph is going to look concave up, like in the picture to the left. And if the second derivative is negative, then the first derivative values are decreasing, and the graph of the function is concave down, like in the picture on the right. One little mnemonic to maybe help remember the relationship between the second derivative sign and the concave up or concave downness of the graph is this. Make sure I get the colors right. So you can imagine a little happy face with plus eyes, right? When you're smiling, you kind of stay positive. So this reminds you that when the second derivative, there are actually two eyes too there, so to remind you of second derivative, is positive, then the graph is going to look something like this smile right here. Or you can imagine if it's just by itself, you can imagine it being a cup. So you might say it's concave up like a cup. So this happens when the second derivative is positive, you have a picture that looks something like that. It's either going to be bending, in this way it's either going to be decreasing and bending along the cup or the smile, or it's going to be an increasing graph bending along the cup or the smile. And then the other one you can draw is concave down like a frown. So down, if it's concave down, then it's part of a frown. This is where the second derivative is negative. Second derivative negative means it's going to be part of a frown. Just like that. We'll see this coming up when we do our examples and we look at where the first derivative is positive and negative, and then look at the graphs that result. Now, where might the graph change from concave up to concave down, or vice versa? Well, those are going to be the same places where any value changes signs, and that's going to be where the second derivative is 0 or where the second derivative does not exist. If you think back to packet 14, these were the two cases we looked at for the first derivative changing signs. Where is the first derivative equal to 0? Where does the first derivative not exist? That's where the first derivative could change signs. And here it's the same thing applies to the second derivative. If you want to know where the second derivative changes signs, look for where it's 0 and where it does not exist, and it could change signs as you cross those x values that make that happen. So let's go ahead and look at example 1, which says find the intervals of concavity of f of x equals x to the fourth plus x to the third minus 3x squared plus 1, so this polynomial. We have a picture to the right, but most of the time you're not going to have the picture. You just have to figure this out algebraically. At the end, we'll use the picture to confirm that what we got was right. So what we need to find the intervals of concavity, with concavity meaning concave up or concave down. It doesn't mean with cavity, concavity, cavidad. I'm not sure if that's how you say it. It's concave up or concave down. So up like a cup or down like a frown. It's how the graph bends. So it's going to find the intervals where the graph is concave up and the intervals where the graph is concave down. All right, so to get that, we need to get the second derivative. That's what's going to tell us whether or not the curve is concave up or concave down. But to get to the second derivative, we need to go through the first derivative. So we're going to take the first derivative. Here we have 4x cubed plus 3x squared minus 6x. Hopefully these derivatives are getting easier and easier to process, especially the polynomials where you just are multiplying those powers down. And if not, keep practicing and they'll come to you. Then we take the second derivative. So that's going to be 12x squared plus 6x minus 6. And in a moment, we're going to be figuring out where that's equal to 0, so it'll be nice to have it factored. So what can we pull out here? Looks like we can pull out a 6. And then factor what's remaining. So the 2x squared will have to break up into 2x and x. Then you've got 1s. Those things, those are the only two numbers that multiply to 1. And so this one will have to be positive, this one will have to be negative. That makes a positive 2x and a negative x, which gives you plus x inside. Okay, so now what we're going to do is figure out where the second derivative is equal, and maybe if there's any place where this derivative does not exist. We'll always look at those two cases. Well, the first derivative, if we set that equal to 0, we already have it factored, so that's not too bad. That's going to be 0 at x equals half. All right, set 2x minus 1 equal to 0 and solve. And you get x equals a half. And then x equals negative 1. And for the second derivative does not exist case, well, there aren't really any x values that would make that happen, because if you plug in any x value into the second derivative, you get a value. There isn't any division by 0 or any kind of natural logs that might have domain constraints. So here we would just say something like none, or nowhere, or something along those lines. There aren't any x values where the second derivative does not exist. Now what we're going to do is figure out the sign of the second derivative. So we'll make a number line, put those x values that we found online. Make a row now for the second derivative, which was 0 at those values. And then do a sign analysis on the second derivative. So this row is the outputs of the second derivative here that we're capturing. It was 0. The output of the second derivative at -1 is 0, and at 1/2 is 0. So now we can pick some x value inside of the first interval, like say -2, plug it into our second derivative, and let me just do a little work on the side for that. So -2, if we plug it in, we're going to get positive 6 times, and then -2 times -2 is -4, minus 1 is a negative number, and then -2 plus 1 is a negative number. Overall, we have an even number of negative factors, which gives you a positive sign for the second derivative. Will the sign flip as you cross x equals -1? Yes, because the x plus 1 has an odd exponent, so the sign will flip. Odd multiplicity. Will the sign flip as you cross x equals 1/2? Yes, because 2x minus 1 has an odd exponent. Again, if that is unsettling to you, you can always plug in x values, but I definitely encourage you to learn how that works. Think about, as you cross this x value, what is it that's changing about these values? And you'll quickly come across, well, x plus 1 is suddenly going to flip from being a negative number to a positive number, and that'll flip the overall sign of the expression. Okay, so now we know the sign of the second derivative on every interval, and we're interested in what are the intervals of concavity, so let's use that sign analysis to figure out where the curve or the function is concave up and concave down. Can't seem to spell concave. So concave up and concave down. Well, the curve is concave up, or the function is concave up, when the second derivative is positive, and that happens on two intervals, from -infinity to -1, and from 1/2 to infinity. And then the curve is going to be concave down, like a frown, when the interval is between -1 and 1/2. So those are the intervals of concavity. These are the intervals of concavity. Now let's see what that looks like on the graph. Go up to the graph again. So this is the picture of f of x. And you'll notice that from x going from -infinity to -1, so all along here, up until about this point right here, the graph, I'll just shade that part, the graph is concave up. It's like part of a cup. I mean, a really steep cup with a really long side. Very impractical cup, but it's like part of a cup, right? It's in the shape of a cup or a smile. So this is where it's concave up. Then, as you go from x equals -1 to 1/2, the second derivative is negative, which means the graph is concave down. So that's going to be from about here to here. The graph is concave down. There, it's part of a frown. You can see the frown right there. Concave down, part of a frown. That's what it's going to look like when you have the second derivative negative. And then from 1/2 to infinity, the graph is concave up. Notice that it's part of a cup again. Concave up. So that matches exactly what we're seeing. Now, just as a preview of the next part, these points right here, and here, where the graph changes from concave up to concave down, are called inflection points. Those are called inflection points. And in fact, let's just actually head right into it. So there's an inflection point right here, because I know you can't wait. There's an inflection point right there. I picked the wrong color. Right there and right there. Those are inflection points. They're changes in concavity. So that's what the note on page 2 is saying. A point C, f of C, where the concavity changes, so either concave up to concave down or concave down to concave up, is called an inflection point. And these are going to happen if these could happen if either the second derivative is 0 or the second derivative does not exist. That's how we found those x values in the first place, where we had those sign flips for the second derivative and therefore potential concavity changes for the function. So here's an example of a graph, and I just wanted you to practice finding the inflection points. So remember, it's a change in concavity. It's not going to be a max or a min. It's something different. So think about going from a cup to a frown. Where does that happen? So concave up like a cup to concave down like a frown. Where would that happen? Or concave down like a frown to concave up like a cup. So where would the first x value be where you have an inflection point, roughly speaking, on this graph? So if you said x equals 4, that would be correct. Right there, the graph is changing from concave up to concave down, part of a frown. Where's roughly the next x value where we have an inflection point? So if you said right around x equals 7, right about there, then that would be correct. That's where the graph is changing from concave down to now concave up, part of a cup. What would be the next inflection point? If you said right about here, at maybe a little after 11, so between 11 and 12, then that would be correct. It's very easy to want to say that at 9 there's an inflection point, but notice that the concavity doesn't change as you cross x equals 9. It's concave up on the left of 9, and it's concave up on the right of 9. It's only when you get to right after 11 that the graph changes and is concave down. So all three of these are inflection points. Another way, by the way, that can help you identify if a graph is concave up or concave down, and some people find this helpful, is by thinking about where the tangent line is. If the tangent line is below the curve, like this, if it's below the curve, or like this, then the graph is concave up. So if your surfboard is below the curve, then it's concave up. Whereas if your surfboard or your tangent line is above the curve, then it's concave down. So either way you like to think about it, you can think about it as part of a cup or part of a frown, or tangent lines below the curve means concave up, and tangent lines above the curve mean concave down. Either way you want to think about that is great. In fact, it's good to think about it in both ways. Let's do example 2, where we're asked to find the inflection points of the polynomial that's given. Now, when you see that word inflection point, immediately you're going to think, I need to get to the second derivative. So inflection point is like a key word that says, find the second derivative. That's going to help you get inflection points. So to get to the second derivative, we need to go through the first derivative. First derivative will be 15x to the fourth minus 20x to the third. Second derivative will get 60x to the third minus 60x squared. We'll go ahead and factor to get ready. Then we'll set this second derivative equal to 0. figure out if there's any place where the second derivative does not exist. Always think about those two, in case there is a place where the second derivative does not exist. So here we have the factored version of the second derivative, which is 0 at x equals 0 and x equals 1, looks like. Then we make a little, and then the second derivative does not exist. No place that could happen because this is a polynomial for the second derivative. We'll just write none. Now we'll put those x values that we found on a number line and make a row for the second derivative, which was 0 at each of those x values. Then we can start things off by plugging in an x value into the second derivative. I'll just plug in like -1 to start us off. Here we get positive 60, I'll include it in there. Just in case that's ever a negative number. If that were negative 60, we'd want to write that there's a negative factor in there that's flipping signs. But this is positive 60. This one, if you plug in -1, when you square it, it becomes positive 1. So that's going to be a positive, positive x squared. And then when you plug in -1 to the x minus 1, you get a negative factor. So overall, it looks like we get a negative value for the second derivative. Now, is the sign going to flip when we cross x equals 0? The answer is no, because the factor x that the x equals 0 came from has an even exponent, and so there isn't going to be a sign flip. If the factor x flips signs, it doesn't matter because it's squared, and so there wasn't really a sign flip after all. So no sign flip as we cross x equals 0. In fact, if you were to plug in a value between 0 and 1, like a half, in, then you'd still get positive factor times positive factor, because the x squared is still positive, times a negative factor. And so nothing has changed, so the sign overall doesn't change. Will the sign flip as you cross x equals 1? Yes, because x minus 1 it has an odd exponent, and it'll flip the sign of everything. So now we know where the curve is concave up and concave down, but we were asked to find the inflection points. Those are the points where the concavity changes. So 0 is not going to be an inflection point, because notice that the concavity doesn't change. It goes from concave down to just concave down. Nothing changed. But 1 will be an inflection point because, number 1, it's a point on the graph. The function is defined at x equals 1. And there's a concavity change there from from concave down to concave up. So the inflection point is going to be at 1, comma, and then to get the y value, we plug it back into the original function. So 3 times 1 to the 5th minus 5 times 1 to the 4th minus 1. There, each term becomes its exponent when you plug in a 1. And so you just get 3 minus 5 minus 1, which is -3. So there's the inflection point. And I'll point out, the inflection point. There's the inflection point. All right. Inflection point. Notice that the concavity is changing from concave down to concave up, just like we found. Thank you for watching this video, and see you in the next part.